Hey everybody, welcome back to Chapter 7, where we are looking at relativity. I will start today's lesson by just reviewing the sort of 5 stages of relativity that we chatted about in the last video. Remember that this is a crazy chapter in terms of the information that I'm going to present. And here are the 5 sort of stages or feelings that you may go through. You may experience them all right in order. You may skip over some if you're lucky. Maybe you go right to acceptance if you're the kind of person that listens to a teacher say something and says, yeah, okay. Or if you're the kind of person who wants to know why, then you might get stuck in some of these stages, like stage 3, bargaining. So just put those up there for fun. Again, we'll point out when we meet in Zoom, sort of where people are at in terms of their dealing with relativity stages. So what we're going to do today is continue on last day, or continue from last day, where we left off here. We had talked about the Doppler effect. We talked about how Michelson and Morley set up an experiment and spent years and years and years looking for luminiferous ether. And they found out that it didn't exist. Maybe you got a little bit angry at me, but we now sort of have a glimpse as to how they felt. And that came up with 2 assumptions of relativity. There is no preferred reference frame for light. We finished off the last video saying that really means that you can't tell who's moving and who's stationary. And that's crazy, right? Like you can't tell when you get in a car if the car is moving relative to the road or if the road is moving relative to the car. That's where this name of relativity comes from. All we can say is that things are moving relative to each other. But we don't actually know who's truly doing the movement in terms of like their position in the universe. The other weird assumption of relativity that we figured out is that light is special. It always goes the same speed no matter what. Doesn't matter if you're moving, the thing emitting the light is moving. If you have a radar gun and you go to measure the speed of light, you will always measure 3 times 10 to the 8 meters per second. And we use that number so often that it gets the variable c. Now, a couple of definitions I'll get you to scribble down. These are ones that I will keep referring back to, and I'm not going to make you regurgitate these definitions on the next test, but you do need to sort of have these in the back of your brain to understand some of the thought experiments that are coming at you in the next few videos. The first one is when we say reference frame. And we already said that right up here, right? There's no preferred reference frame. A reference frame is, physicists would call it a platform to make measurements from. I like to think about reference frames like this. They are just points of view. So a POV. It's like the world through your eyes compared to the world through my eyes. Those are 2 different platforms, 2 different points of view that we could take measurements from. And what relativity says is when you're dealing with light, there is no preferred reference frame. What you believe and what you see in your point of view or from your platform is just as good as what I see. So if I run by you and you're standing on the side of the road and you say, oh, Heinrich, look, you're moving. That's from your point of view. But maybe from my point of view or reference frame, I say, no, I'm stationary, but you're moving. And there is no preferred reference frame when we're dealing with things moving. So we are both equally right. We kind of have to agree to disagree. So that's the first definition. Reference frame just means a point of view. The other definition that we use is when we talk about an observer. We make it sound like it's a singular thing. But when Einstein, we'll see he jumps in here, he came up with all kinds of crazy thought experiments and came up with all kinds of crazy ideas. When he says an observer, when we say an observer, we don't actually mean a singular person. We mean a whole bunch of people standing in a line, and they all have clocks that show exactly the same time. All of their clocks are synchronized. So that's kind of weird, but just sort of work with me. So what I want to do is, based on those 2 assumptions of relativity, no preferred reference frame for light, aka you can't tell who's moving, and the speed of light is always the same, it's always 3 times 10 to the 8 meters per second, I want to look at some of the sort of results of those two things. So the consequences, the first one is something called simultaneity, and all of these consequences were figured out by Albert Einstein, and some of them he had some help from a friend named Henry Lorentz. And Einstein kind of just sat around and came up with these really wild thought experiments and said, well, here's a weird way to think about it. He was kind of bargaining almost. If you think about it this way, then it would have to be true. And if it's true in this scenario, then it has to be true in all these other scenarios as well. And I want you to keep in mind that all of these results that Einstein came up with, the first one being simultaneity, and we'll kind of tackle 1 or 2 per video, they have all been proven now. In Einstein's time, they couldn't really prove a lot of this because nothing could move close to the speed of light. But now we have particle accelerators. And their sole purpose is to take little bits of matter, get them going close to 3 times 10 to the 8 meters per second, and then typically we smash those little particles into other small particles, sometimes to purposely make radioactive materials, or sometimes just in the name of science to see what happens. And all of Einstein's ideas and results have been proven true. So I want you to keep that in mind, that these are not like unproven ideas. These have been proven over and over and over again. And if they're true of small particles, then they've got to be true of collections of small particles. So it would be true for you and I if we could make ourselves go that fast. And that part we haven't figured out yet. But we'll talk more about that in the next video. So simultaneity, I'm going to get you to scribble this down, talks about whether 2 separate events occurred at the same time. So here's the setup. We're going to go with somebody standing on the ground and somebody standing on like a little train cart of some kind. And we don't actually know who's doing the moving, right? Remember, we could say, oh, the train's going to move to the right, or is it actually the ground moving to the left? Wow, it doesn't really matter. For this example, let's just say that the train is moving to the right at half the speed of light. That's really, really fast. And what's going to happen is when this train cart goes by this person standing on the ground, these 2 people are going to give each other a high five. Now, what I don't want you to do is sort of spend the rest of this video thinking, holy cow, what would it feel like to give somebody a high five if you were going at half the speed of light? That would really, really hurt. Like, would it break your hand? Would it vaporize your hand? Would you go to give somebody a high five and bang, and then all of a sudden you've got a stump because it just like ripped your hand right off? Those are valid concerns about giving a high five if you're moving that quickly or somebody's moving that quickly, but you can't get bogged down in the details, right? So you really got to try not to get bogged down in those kind of thoughts. So we're going to leave those alone. We're going to say that there's this high five. Now, hopefully you can wrap your head around this as well, that everything you see is actually an event that's happened in the past, because light has to travel from that high five towards your eyes. And it's traveling ridiculously fast, right? 3 times 10 to the 8 meters per second. But there is this lag. So as these people give each other a high five right here, the image of the high five, the light bouncing off of their hands when they give each other the high five, is going to spread out in all directions. And eventually that image is going to hit the person's eye and they're going to see the high five. But there is this very slight delay. It's just like how they say that the light coming from the sun, what's the number? It's like 7 or 8 minutes or something like that. It takes the light to get from the sun to Earth. It's traveling really fast, but it's got a huge distance, right? So there's this delay. So what's going to happen in this thought experiment is these people are going to give each other a high five, and they're going to set up some camera detectors. And we're going to try to figure out in which order do the cameras see that high five. So like, do all 4 cameras detect the high five at the same time? Is there differences? And if there's differences, does it depend on your reference frame? Does it depend on your point of view? So I'm going to switch over to a PowerPoint now because you really need to see things move. There also is, if the PowerPoint doesn't quite do it for you, I'm going to post a YouTube video with this lesson, and you're going to want to watch it. Let me just double check what the sort of timestamps are. So double checking the video, it's called The Mechanical Universe, the Lorentz Transformation. You'll see it posted right beside this notes video. It is this example in a really bad old animation, but it works. You want to watch the video from right around 7 minutes to 10 minutes. So it's only like 3 minutes long. But if you watch the video from the 7-minute mark to the 10-minute mark, that'll show you this sort of like in a full animation, and it might help it make more sense. I can't sort of make a video of the video. This program won't do that. So instead I've got a little PowerPoint. So let me show you how this works, this thought experiment that Einstein came up with. So we'll switch over to this. So Physics 11, Special Relativity, looking at simultaneity. Which of those camera detectors see the image of the high five, and in what order? So here's our two people. We've got Albert Einstein and Henry Lorentz, the sort of two guys, the fathers of relativity. And here's what we're going to have. Hopefully this is filming okay. We're going to say that Albert's on the ground and Henry is on that little train car, and it's going to move by at half the speed of light. So there's the image of the high five. Let's imagine they've taken their hands out of their pockets. They give each other a high five. Don't worry about whether they vaporize their hands or not, because that doesn't really matter, although it would be a concern. So there's this image of the high five, and they want to figure out sort of which order of the little camera detectors. So I don't know why there's little guys in spacesuits, but there's 4 cameras there. We had called them A, B, C, and D in our notes. And we want to see which cameras detect the image of the high five first. So there's the sort of expanding image, right? So the little explosion symbol represents right at the instant of the high five, and then this circle is going to expand outwards and grow. There you go. It's going to get bigger like that. We want to figure out which camera detectors see that image first. Now, if Henry and Albert are both stationary compared to each other, if nobody's moving, then all 4 of those cameras would see the image at exactly the same time. They would see it simultaneously. But what if somebody's moving? Remember, we don't really know who's moving, so we'll chat about that here. Let's take Albert's point of view first. So there's what the image looks like from Albert's point of view. He thinks that he's in the center of this expanding circle, right? Now, what's kind of weird is the light's traveling outwards from right where Albert's standing. It's traveling outwards at the speed of light, but Henry's moving really fast. So let me play that again. You're going to see the image expand. This is Albert's point of view. The image is going to expand outwards. Albert's going to be at the center of the image, but he thinks Henry's moving to the right. So let's try that again. And hopefully you can see here that what ends up happening is this camera is sort of moving into the circle. So this camera is going to see the image first of the high five. And then these 2 cameras sitting on the ground with Albert, they're going to catch the image simultaneously. They'll see it together. And then this camera right here is going to catch it last. It's kind of running away from the image as it expands outwards. So I'll show you that one more time. One camera moves in, 2 cameras get it simultaneously, and then that 4th camera catches it at the end. So that's Albert's point of view, right? Albert Einstein in on this, sort of going, hey, just think about that. There's one point of view. Now, what if we ask Henry? Because remember, all points of view are valid. They're all equally good. There is no preferred reference frame for light. So Henry says, no. I'm at the center of the circle, and it's actually Albert moving to the left. Henry says, I'm not moving at all. Maybe it's just the ground moving to the left under my feet like a giant treadmill, right? Or under the wheels of the cart. So now we're going to flip over to what Henry sees from his point of view. So he's now going to be at the center of the circle, and it's going to expand outwards according to his eyes, his reference frame. So now he believes Albert's moving to the left. There's what it looked like. And again, it's kind of quick. Let's see if you can catch it. We'll do it one more time, and then we'll talk about which detectors or which cameras see it first. This is Henry's point of view. He's at the center of the circle. High five. Image travels outwards. So it was actually now this camera that catches the image first. It was moving, whoops, into the picture. These two cameras on Henry's train with him, they see it second and they see it at the same time. And then it was actually this last camera out here that's going to capture the image last because it's kind of running away. So what's crazy is that Albert Einstein came up with a thought experiment like this, right? It is, I think it's crazy. It's quite amazing. His brain thought about things in ways that regular people like you and I guess I'll put myself in the regular or under the regular umbrella, but that's debatable. His brain worked in different ways. Oh, one more. There's Albert's point of view. And here's Henry's point of view. There is a difference in terms of the order, in terms of which cameras saw the image first. They each think that the order was different. And you can't say like, well, guys, it has to be one way or the other, because we said in relativity that all points of view are equally valid, right? They are going to have to agree to disagree on the order in which those camera detectors captured that image. Albert Einstein, man, totally crazy that he came up with this thought experiment, but it's super cool. Let's flip back to the notes and summarize that. So from the ground point of view, actually I can full screen this, I think. So from the ground point of view, this was Albert's point of view, with the image sort of in the center of his position, was that if you label these as A, B, C, and D, as we've done here in the notes, camera C moves into the image and sees it first. Then A and B go together, and then camera D goes third. That was Albert's point of view. Now, Henry's point of view from the train was a little bit different. He said, no, I'm stationary and the ground is moving to the left. I'm at the center of the image. So he sees camera B get triggered first because that camera is moving into the image. Then C and D get triggered together. And then eventually the image catches up with camera A because it's kind of running away. So again, look at these orders, right? C first, A and B second, D third. B first, C and D together in second, and A third. And the sort of result of that is who's correct, right? What's the order? And the answer is yes. And that's going to bother some of you. Some of you right now are going to go, no! And you're going to go into denial, right? And that's okay. But we truly do have to agree to disagree. The result of this wild thought experiment is that simultaneity, did things happen sort of together different times? It's totally relative, right? It depends on where you measured from. It depends on what you saw from your reference frame. So again, the answer kind of sort of, what was the correct order? Was it C first, then A and B second, then D third? Or was it B first, then C and D second, and then A third? Yes. You're like, what? No. Which one was it? Yes. What do you mean? Was it both? Yes. No, it's got to be the ground point of view. Nope. It's got to be the train point of view then. Nope. You're telling me the correct order is both points of view. Yes. Right? It's weird. It takes some time to wrap your brain around that. But there is thought experiment in result number 1. I think it's super crazy, but super cool. I think it makes sense. Again, you can scroll back. You can watch that video. from 7 minutes to 10 minutes. Watch the whole video if you want. It's pretty cool. But this specific simultaneity issue is covered in that video from 7 to 10 minutes. Now, what I want to do, you'll see in the second box with this result, simultaneity, or this consequence, it talks about doing some relativity calculations for homework, and I want to show you how to do those. The calculations that go with these ideas are really easy. So crazy ideas, but easy calculations. It's kind of a nice trade. So what I want you to do is find, this is in the All Resources folder, you will find a document that looks like this called Relativity Calculations. And you have to know how to do these two calculations in order to get anywhere in this chapter. Because like 90% of the calculations we do are based on being able to calculate these two things. And these two things are beta. So this fancy B is called beta. And then this crazy little fancy looking Y symbol is called, some of you might know this, it's called gamma. And actually when you write gamma by hand, you don't have to do a little fancy Y. Typically when you write the symbol for gamma by hand, it looks like that. It's actually an alpha symbol turned on its side or on its end. I call it the dive bombing fish. So you can go with that symbol typically if you are just writing things down, or you go with the fancy Y gamma symbol if you've got a Word document where you can insert a symbol. So grab your calculator. We're going to talk about what these things are and how to find them. Beta is a calculation where we figure out sort of how close to the speed of light are we going. How close to the speed of light? That's really what we're doing when we calculate beta. And if you look down on this sheet, it actually tells you how to calculate beta right there. It's a very easy calculation. You take the velocity that you're traveling, or that the object is traveling, and you divide by the speed of light. And it spits out a number, maybe something like 0.200. And then mentally what we do is we like to multiply that by 100 to turn it into a percentage. So when you see a beta value of 0.200, I want you to mentally multiply by 100, and that would tell you that this thing is going 20% the speed of light. Right? So we're like 20% towards the speed of light. That's ridiculously fast. There's nothing other than like little particles in a particle accelerator that can travel at 6 times 10 to the 7 meters per second. Cars don't go that fast. Airplanes don't go that fast. Missiles, bullets, they don't go that fast. Not even close. But at that speed, you would be traveling at 20% the speed of light. So what I'd like you to do is grab your calculator and try this with me. And please actually humor me and do these calculations with me. Because if you can't do these calculations, you're in trouble for this chapter. And you should be having a good time with the calculations, not a tough time. Let's make this a bit bigger. Oh my gosh. Finicky here. There we go. So I'll do a couple with you, and then you can find the answer key posted on the website as well. Relativity Calculations Key, I think it's called. So let's try this out. We are simply going to take the velocity listed. So I'm going to go with this first one. 3 times 10 to the 7 divided by the speed of light, which is 3 times 10 to the 8. And the calculator spits out 0.1. I'd like you to, in this column, just to make sure that it's working, let's take 3 decimal places when we do these calculations. So at 0.1, I'm going to list that answer then as 0.100. Which means if I were to like mentally convert that into a percentage, that would be, oops, not 20%, but 10%. So you're going like 10% the speed of light if you're traveling at 3 times 10 to the 7 meters per second. Let's try this third one. 9 times 10 to the 7. So you got to make sure you remember how to type scientific notation into your calculator. Divided by the speed of light, which is 3 times 10 to the 8. You get 0.3. So that object is traveling at 30% the speed of light. You will notice a little pattern. So I'll admit that right now. But I'll let you try a few more. Make sure you double check your answer key. Maybe I'll go down and do like the bottom two here. 2.97. You can see we're getting closer and closer to the speed of light. So 2.97 times 10 to the 8 divided by 3 times 10 to the 8. Ooh, look at that. Is 99% the speed of light. 0.990. And if we go 2.997 times 10 to the 8 divided by the speed of light. Whoa, look at, we're getting really close. Now you've got an object going at 99.9% the speed of light. So that's a really easy calculation. The next one is gamma. And here's what I want you to think of for gamma for now. I like to just call it the weirdness factor. It is the factor by which a whole bunch of stuff is going to change. And I'm not even going to tell you what those changes are, because I don't want to let the cat out of the bag quite yet, as they say. But it's going to be how different things are between reference frames. And in order to calculate that, it shows you how to do it right here. It looks like a confusing calculation, but it's not. You do have to figure out how to type that into your calculator in one shot. That is absolutely key. So I want you to do this one to 6 decimal places, just to make sure it's actually working. So again, humor me, grab your calculator. Let's try this out. Let's try this one right here. We are going to take 1 divided by the square root of. Notice my calculator opens a bracket for me already. You may need to do that if you don't have a graphing calculator, because you want to do this all in one step. It's 1 divided by the square root of 1 minus beta, which was 0.1, all squared. So there's how to run the gamma calculation, this weirdness factor calculation, and there's the number. I'm going to take 6 decimal places. 1.005038. 0.005038. If you can't get this to work on your calculator, then fire me an email or join me on Zoom and we can actually go over it in real time. Let me try another one. Let's try the 0.3. 1 divided by the square root of 1 minus 0.3 squared. So there's the third box, 1.048285. 1.048285. And again, go through, humor me, and actually try them all out, because you do need to be able to do this gamma calculation like instantly. You need to not even be able to think about it. It needs to be the easiest calculation you've ever done. And in order to make it that way, you got to practice it. Let's do the last two, and then you can go check the other answers on the answer key. 1 divided by the square root of 1 minus 0.99 squared. Whoa, look at that. The weirdness factor is getting big here as we start going fast. The differences between the two reference frames would be a factor of 7. So they would disagree like by a factor of 7 on whatever they're looking at. Those coming next lesson, next video, as to what they would be talking about. 7.088812. 0.88812. And for the last one, to finish it off, 1 divided by the square root of 1 minus 0.999 squared. Oh, look at that. Weirdness of 22. Over 22. And again, we're going to see that in the next video when I start sort of talking about what are they disagreeing about, what's weird by a factor of 22, there's going to be some mind-blowing stuff coming at you. There really will. 22,366,272. 22,366,272. So, for practice, please humor me. Finish this worksheet. Make sure you can do this all day long. Finish this worksheet. That's it. that is your homework for this week. For like 2 lessons, that's all. So you've got this to try out for calculations, and that's going to be the basis for most of what we do calculation-wise over the next couple of lessons, which is awesome. Check out that video on mechanical universe Lorentz transformation from the 7 to 10 minute mark. And I will also put a video on there about the Michelson-Morley experiment that you can watch if you desire, if you think that would be something cool to learn some more about. Please hit me up with an email if you've got questions, or join me for Zoom. Zoom preferred, so we can have some group conversation, because this lesson and this unit, super fun. If you can sort of bounce ideas off of each other and hear some of the crazy stuff people will come up with, right? Because really, when people bargain with me, when we get to that stage 3, some of the questions are fantastic, and I might not even have answers, but it's going to make us think about weird things in really weird ways. That's actually really, really cool. So please join me in the next Zoom meeting. I hope you enjoyed these first couple videos. We will chat soon.